Okay, question 5. We've got a question about stopping distance. So we know that stopping distance equals thinking distance plus braking distance. And it wants to know what would make it smaller. So the crucial thing to know is that's a good thing. Okay, if I make the stopping distance smaller, I'm less likely to, say, hit a person that's crossing the road. So anything that sounds pretty good. So it had more passengers. Nope, that'd increase the mass of the car. So that'd give it more kinetic energy. Worn tyres. Nope, it's not going to be able to transfer its kinetic energy to thermal energy as well. It needed new brakes. No, that's pretty bad as well. Definitely have good brakes on the car. Travelling more slowly. That's the correct answer. If the car was going more slowly, it'd have less kinetic energy and therefore the stopping distance would be less. So there we go. On to the next one. We've got a velocity time graph or a speed time graph for the car, and it says use it to find out the driver's reaction times. So what we got here, that's where they've pressed the brakes. This must be where they see whatever it is in the road. So the crucial part is we're after whatever this value is. So now it's can we read the scale properly. So if I just make a neater, oh, I'm so terrible at reading graphs. Let's make a neater one there. So we just got to make sure we read the scale, and each one of these is 0.05. And we can see that because there's 0.75 there, and then we can kind of read back. It's trying to fox you into thinking that each of these mini squares is 0.1, and it isn't. So 0.55, 0.6, that's going to be 0.60. So we're just measuring this bit here. 0.6 seconds. On to the next one. We've got some apparatus to show how the stopping distance depends on the type of surface that it's stopped on. So we're going to get a car on the ramp. We're going to start at the same point. We're going to let it travel down here, and then when it gets to here, the surface is going to stop it, and then we're just going to see whereabouts does it stop. And a higher friction surface should stop it in less distance. So describe an experiment to find out how the stopping distance depends on the surface that stops the car. So we know that our independent variable is going to be the surface. Our dependent variable is the stopping distance, as the distance on the surface. So I'll just put a D there, and then we just got to plan it. So let the car go from the same point on the slope. Measure the distance it travels on the surface with a ruler. So explain the measuring equipment that you need. So I'm just going to underline the word ruler. Next part is, well, now let's change the surface and use the same method above. And the crucial bit is also repeat 3 times for each surface and calculate a mean. We're after any 2 of those marking points. But the crucial part is let go of the car at the same point, measure the distance that it goes on the surface with our ruler. Okay, so now we've got some results for this, and we can see state the anomalous value. So one of these is not going to match, 0.35, 0.32, 0.52. You definitely do not match the others. So that's got to be 0.52 meters. And it says use the results to calculate the average stopping distance. Now the crucial part is, whatever the anomalous one is, we do not include it in our mean. So we're going to use each of these values, 0.35, 0.32, 0.38, 0.33. Divide it by 4, because we've got 4 results, equals 0.345. And then I'm going to make sure that my answer is to the same number of decimal places as my table. So 0.35 is my final answer in here, 0.35, because I want that result to match the decimal places in my table. The next part, one way the student could increase the speed of the car as it reaches the flat surface. So what I could do then, if I go back to that, I can give the car a push, but that might be a bit too variable. Or I can just increase the height of this ramp. I could add more books underneath, whatever it is they've got under there. So going on to that question, anyone, make the slope steeper, push the trolley, add some more books or more things under the slope. And then we've got our next one, which is using A equals V minus U over T. So we just need to know, well, that's my final velocity. That's my initial velocity. So the car is traveling down the slope at 2 meters per second. It accelerates for 4 seconds and the speed of the car increases to 12. So there's my U value, there's my T value, and there's my V value, and I just dump all of that in. So A equals V minus U over T, 12, final speed, take away 2, its initial speed, divided by the 4 seconds, equals 2.5 meters per second squared. And there we go, that's that question done.